today. David did his undergraduate at Cambridge, and then he went actually and worked in the gaming industry, where he co-founded a company called Elixir Studios. And then afterwards, he decided to go back for a PhD in computer science at the University of Alberta. After his PhD, he did a postdoc at MIT, went on to be a professor at UCL for a few years. And since 2013, he has been full-time at DeepMind, where he has been doing amazing work in reinforcement learning algorithm development and applying such algorithms to games like Go and chess and shogi and StarCraft. Of course, he's been receiving lots of awards and honors for this, most recently the ACM Award in Computing for his pioneering work in applying reinforcement learning in games. So we're very happy to have David with us today. And we have a collection of questions, some which were my questions. Most of them actually came from the participants at the school. And so just to kick off the discussion, I wanted to ask you about your decision to go back for a PhD. You're having a very successful career in the industry, and then you decided to go back for a PhD and to study reinforcement learning. So how did you make that decision? What motivated you?
Okay, so thanks, Doina. And first of all, hi everyone. It's really a pleasure to be here, and yeah, looking forward to this chat. In terms of the PhD decision, you know, I'd been in the games industry, but actually for a long time, I think I'd been wondering about the sort of deeper questions of intelligence and trying to understand how we could build something which was really intelligent. And this had been really something which I'd always wanted to get involved in, you know, trying to really deeply understand AI. And I think, you know, as an undergrad, it's really hard to see how you can even go down that path in a meaningful way. And so I ended up kind of in the games industry, and I was kind of involved in making games, and I thought there'd be opportunities to kind of study that question from the context of AI within games. But it kind of became clear whilst developing games that that really wasn't the right forum at that time to be doing this, in the sense that when you're making a game, you really need to deliver something, and the way in which most people were delivering AI that could kind of work was more like scripted systems, and there wasn't much opportunity for open-ended research. And so during that time, I started to kind of look around and came across this thing called reinforcement learning. And when I started poking around, it seemed like, ah, there's the thing, that's the connection to what I really felt deep down AI should be about, you know, this understanding of what it really means for a system to understand for itself how to solve problems. And so something kind of clicked at that moment, and it was kind of then that I felt that I would really, you know, I felt I knew what I kind of wanted to take as a next step. And so, yeah, I left the games industry and managed to find a kind of connection to my next career by, you know, coming to the University of Alberta, where they had a lot of expertise in actually applying AI to games, board games in particular, and started working on reinforcement learning in the game of Go.
Thank you very much. So you mentioned your motivation as understanding intelligence and wanting to build intelligent systems. What do you think is the role of reinforcement learning in building AGI, artificial general intelligence?
Yeah, good. So I guess I see reinforcement learning as the essential problem, like the real formalization of what we actually need to do in order to make an intelligent system. That, you know, for anything where you really want to have you've really got a problem and you've really got some goal that you need to try and achieve out there in the real world, that reinforcement learning is kind of the formalism which gets closest to that real thing, which either natural intelligence is having to do, or, you know, when you've got an animal in its environment and it's trying to figure out how to survive in that extremely complicated environment, and there's all these things it needs to do in order to do that, or whether you've got some robot that's trying to achieve some goal that we've given to it. You know, in any one of these really rich cases, it feels like the formalism that best captures what we really mean by intelligence, a system that's actually able to achieve all of these kind of long-term goals that we'd like our AIs to be able to do, is the RL problem. And so I guess, you know, you could think of this as almost like a hypothesis that the RL problem is actually the problem that captures everything we need for intelligence within that one formalism. And so if that's really true, well, by studying that one problem and finding ways to solve that one problem, we may be able to go an enormous distance and possibly even all the way towards general intelligence.
So you mentioned that RL captures the problem of intelligence very well. What are the challenges in using reinforcement learning for AGI? And some of the participants were wondering, is it because there's multiple data modalities in sort of general intelligence and maybe it's hard to relate those to each other, or are there other issues that are perhaps difficult?
I guess I don't see the modalities as like an inherent, like fundamental issue. Like there's going to be some agent and it's going to be bombarded with this stream of sensation, and those sensations may come from, vision or audio, or it might be robotic sensors, or whatever that data is. Our agent's going to be inhabiting this sort of sensory motor stream of observations coming in and actions going out. And we better be able to deal with really complex streams with a lot of structure. And that structure, yeah, maybe it comes from the nature of whether it comes from vision or audio, but inevitably, even within one of those streams, there's going to be immensely complex structure that we need to figure out and be able to sort of parse that stream. So I think the challenges are common, really, to no matter what the modalities are. And I think some of the big challenges we have in really, if we really pursue this all the way towards general intelligence, is like you think of human intelligence or something. We're able to deal with lifelong learning over long time scales, where we kind of the agent is born and starts being bombarded with these sensations from the first moment of its life, 70 or 80 years or whatever, and it has to just keep learning and building and constructing knowledge and understanding how to parse this kind of rich stream of experience and do better and better and better. And I think that really is the challenge. I think we've made a lot of progress in understanding how to deal with problems on kind of shorter timescales, and where there's a lot of it feels like, yeah, long lifetimes feels like a big next step to take.
So on the sort of flip side, there's practical industry problems. And so participants were wondering if you see for RL a future of broad applicability and applications in industry. And, is RL adopted outside academia? Where is RL adopted outside academia from a practical point of view?
Yeah, so this is a great question. I think many of us have this sense that there's an opportunity for RL to do much more than it's doing right now. But I think already we see versions of the problem. Like if you think about adaptive control, or there's a lot of systems in the world which are actually controlled by reward optimizing systems. And I think in many of those cases, okay, for now, the model has sort of been built in by people, saying that this explains how the dynamics of the systems work. But I think going on, it feels inevitably true that we must be able to build more and more applications where the system learns for itself through experience what how the world works, what the model is, how the dynamics of this system operate. So concrete applications, okay, let's get concrete. Where do I see there being future applicability of RL? I mean, I think there's really exciting chances to transform healthcare one day. This is a big challenge if we could crack it. There's all kinds of issues in terms of privacy and safety and so forth. But really, imagine in 30 years or whenever we have a system which is really able to help people live longer and healthier lives through understanding, through a trial and error process of learning how to do better and better and better. I think it's also inevitable that we'll see RL coming in more and more into a lot of the online interactions that we use online, and I think we see early instances of this right now, where there's widespread application of things like bandit algorithms in recommender systems and so forth, which are giving people suggestions about what they should look at on the net. And I think this is just the beginning of kind of moving towards things like assistants, digital assistants, where where there's actually something which is, starting to understand what we as people want and how to interact with them and do better and better.
Just as a quick follow-up, are there any things that we should do in terms of reinforcement learning research in order to foster practical applicability in industry?
Yeah, that's a great question. I think right now, maybe one of the biggest things we can do is make it easier to use RL, to have something which out of the box just kind of works. And I think we all know that right now, RL is something where, yeah, you can make it work in your problem, but you have to do a lot of dedicated tuning and figuring out exactly how to tailor this particular instance of RL, of your RL agent to work for your particular problem. And I think that in order to have widespread applicability to a huge range of different problems, I think we need to move beyond that to RL systems which just work. And it should be the case that we shouldn't have to be the ones answering the question of what's the next application, that we should be surprised by what comes next, because we just make it so easy to use RL that we, people surprise us, and it's like, wow, look, someone's used this to solve some, difficult problem in crop rotation or something, in which we weren't even aware that there was a critical need for this thing, and yet by making it easy and widespread, I think the nature of intelligence is that there are a huge number of applications. We see that in all the things which us people can do, and the more intelligent we can make our systems, the greater the impact that they can have. But they need to be able to just kind of they need to be able to work without years of continual intervention on our part to get there.
Thank you. So, of course, you have worked on large-scale reinforcement learning agents, AlphaGo, AlphaZero. You have a lot of experience in building such large-scale systems that can become really, really successful at their task. What are the most important challenges in doing this? Is it the engineering effort? Is it are there any things that you found particularly either difficult or really exciting in this kind of effort?
So it's a great question. I've always tried to focus on scalability, like finding the ideas which have legs to them, something where try and identify the ideas where, as you scale up the amount of data that you can generate, the experience that the agent kind of sees in this environment, you can do better and better and better. And so it feels like that's the challenge. Like the challenge is how do you design a Go playing system which just keeps getting better as it sees more and more games of self-play, or how do you design a robot which keeps improving as it starts to have more and more experience in the world. And these are the real challenges where I think if we can find those ideas that help us to kind of, which have legs that enable it to just keep doing better and better and better, that sort of inherent scalability, then as we pour in more resource into the system, it should do better and better and better. And now that resource can take different forms. It could be experience, which I mentioned, which is kind of maybe in some sense the most precious resource, or sometimes the most plentiful. It could be computation, or it could be the memory of the system, and maybe even other resources. But it feels like the success of deep learning is really due to the fact that it's something which scales effectively with those three resources. That as you give your systems more memory, build bigger networks, you give them more data, and as you start to give more computation, you train them more and more and more, that the performance just keeps going, in the sense that you look back at the learning curves we had in the 80s and the learning curves we have now, they kind of just look like a zoomed in version of what we used to have. Like, the things that we're learning back then, you come back to them now and okay, the amount of data that they're seeing is orders of magnitudes greater, but the curves are kind of still going up with roughly the right shape. And so if we can find those things for RL, then we're in a good place. And so I think that feels like the key challenge. And if we can just crack that challenge, we're in a good place. So concretely, what does that mean? well, it's hard sometimes, it's hard. And I think one of the things we can do when we're facing a real application is to simplify the challenge and make it easier to take those first steps. So it might be that we, I always start by solving a simpler problem than the real thing we want to do. So, and you can simplify in many ways, but one way you can simplify is to try and just make sure that each piece of your system is working really well in smaller instances of the problem you actually care about. Or even, for example, if you're trying to get the architecture right or something, make sure that at least what you're doing makes sense in a supervised learning context, to make sure that all of the pieces work before you go to RL. And that's not to say that you need the supervised data, but just like a sanity check, just make sure as many simple steps work first before you add in the complexity of doing the bigger and bigger things. Because these bigger challenges, they're really hard, and inevitably the first thing you try to do, if you build some really complicated system and just try to run it on that big challenge, it's not going to work. And you're going to throw up your hands and say, well, this didn't work, and why? And you'll end up scratching your head and not being sure. Whereas if you start simple and then build up, you kind of gain confidence at every step that what you're doing is right. And maybe the other thing is just keeping focus, that it's set clear goals of what you want to do and keeping focus on those goals. And sometimes you need to focus on those goals for years to to really crack it. But that's, research is hard, it's and fun too, luckily.
That's really good advice. Thank you. And that's actually a good segue to the next question, which was coming from one of the participants. There's many of these algorithms, let's say AlphaStar, which have very large, complicated neural nets, and they use all kinds of training tricks, right? We use replay buffers and target networks and various ways to stabilize and regularize. So you have any further suggestions for choosing architectures and algorithms for training deep RL agents successfully? So you mentioned sort of starting small and validating your ideas, perhaps in a simpler problem. Are there other is there other wisdom regarding how to decide on architectures and algorithms?
I mean, maybe let me say one new thing and then just reinforce what I was saying before with an example. So the new thing, I think, would be to kind of tie break towards minimalism. That it's often the case that more complicated ideas, well, the more complicated pieces you put in, well, they might seem to be kind of working together in a way which is doing better on your current measure of progress, but then probably something's going to change, and you're going to end up, getting to a new part of your problem that you hadn't seen before, or dealing with some new issue that's arisen. And will that same combination still be effective? And so I think just a general principle is to try and keep things simple, and the simpler they are, the more likely they are to kind of have longevity and really work across many different situations. And then just to make it concrete, the previous example, I mean, what we actually did in AlphaStar was we really set sub-goals that corresponded to different ways to simplify the problem. So when we were working on things like the architecture of the neural network, we tried to first of all understand that in the simplest context, which was just pure supervised learning, and at least get a sense of what architecture was effective in supervised learning before we then move on to the next level of complexity. And then we focused on the RL problem by holding the opponent fixed and just trying to find like a best response to that opponent. And that's then a pure reinforcement learning problem. And how do you then solve that pure reinforcement learning problem as effectively as possible? And that, we looked at a variety of different RL updates in that context. And then there's this question of, well, how do you then, deal with aspects of self-play and all the different agents which are involved? And we had a third layer of complexity of trying to understand how to build up a multi-agent system that's effective. And then finally, the fourth and final level was actually what we were trying to do, which is, playing against real people on BattleNet. And so for that, there's a whole new set of questions which arise. And at every level, you need to know that what you've achieved on the level before is really going to generalize to the next level. But at least by starting there, you isolate your problems more easily in terms of a researcher and figure out, whereas it's much harder to isolate what's going on with your RL update if you're already trying to play on BattleNet, and it's almost there's too much going on.
So on a related note, sometimes there's the perception, sometimes there's the reality that deep RL algorithms can be difficult to train, right? There can be instability. Sometimes there's issues with sample efficiency. We just need lots and lots of experience. So how do we solve these? Or do you see like particular research directions that would be really helpful, both in terms of the stability of the training process as well as the sample efficiency of deep RL?
Yeah, I mean, I think this is really getting to the heart of what's important in deep RL. I think we've made progress with our core algorithms, and some of that progress has come from really simple observations about what makes the update more stable, and often that ends up being reflected in better performance and better scalability. But almost certainly we're still closer to the beginning of that journey than the end, and there are clearly far better reinforcement learning algorithms that are out there. So I think in terms of sample efficiency, it feels like the obvious direction to explore there is model-based reinforcement learning. That if we can build and exploit a model effectively, that might enable us to make better use of the rich feedback that we have in terms of all of the other observations that are in the environment, rather than just focusing on reward. I think that's, maybe more generally than model-based RL, is this idea that there is a rich stream of observations coming in that contains more than just the reward. And although the overall problem is to maximize reward, the way in which we solve that, if we want to be sample efficient, we should be sure to make use of all of the information that's contained within that stream of experience to do that effectively. And there may be other ways to leverage that. So in terms of stability, one of the things we've been exploring recently is whether it's possible to encourage the system to learn for itself what's stable, and maybe this is kind of passing the buck in some sense and saying, well, I don't know how to answer your question, so let me build a system that does. But maybe it's possible through a form of ongoing meta learning to kind of basically start simple, and then learn over time what updates are the most effective, so the system can learn for itself how to ultimately achieve the most stable and therefore most effective performance. I think it's a great question. I think there's many other approaches. I don't want to pretend that that's the only way. I think theory has clearly a strong role to play in understanding stability, and I think there's a lot of insights yet to come. And I'm very excited. You see the whole field taking off with loads of super bright people coming into it, and I think there's just this whole world of new insights to be gained and discovered.
Yeah, so I was actually going to ask you about theory, but since you mentioned that, just as a quick follow-up, if we look at the history of RL, let's say with function approximation and so on, traditionally we have brought in ideas from supervised learning, and then we have made them work with what's essentially reinforcement learning loss functions, reward prediction, error, and so on. Do you think that there is a need perhaps to revisit the optimization specifically in the context of RL, or to revisit the question of function approximation specifically in the context of RL? Do we need architectures and optimizers that are designed for RL algorithms, or can we continue to do what we're doing now, which is to take the best from supervised learning and just try to use it more or less off the box with our own loss function?
Okay, that's a great question. Let me try and say it this way. I think there's an awful lot that we can learn from supervised learning, but it can't be the end point for the following reason, which is that the fundamental nature of the reinforcement learning problem is interaction. It's about an agent that interacts with its environment so as to continue to try and do better and better and better and better. And so you might ask, well, what if someone just gave you this enormous data set that contained like everything you ever needed? Would you need interaction? Would you actually need the RL problem? Or could we just from this giant data set kind of apply our best learning algorithms and our best, use our best theory and our best whatever we could on that big data set? And it feels like the answer inevitably has to be no, that no data set can be sufficient. And the reason is that the problems we want to solve are really complex, and they're much larger than you can capture in even a huge data set. The space of possible things you can do in the world is massive. You think about humans, they might be born in the Arctic, or they might be born in the Sahara or in the rainforest, and the space of kind of knowledge that they need in order to deal with those kind of different unknowns, the space of potential knowledge that they need is vast, and much vaster than anything which could be contained in that initial data set. And so the other way to say it is that if you have a data set and you try to do well on that data set, there might be a lot that you can learn from it, but inevitably there'll be generalization error. Inevitably there'll be generalization error because the world is just so big. And so what are you going to do? Are you going to just accept that generalization error, or are you going to correct that generalization error? And the special thing about RL is that it's interactive. Through this interactive process, the agent can learn to correct its generalization errors. So if it finds itself in the rainforest, it can start to climb trees and understand what the nature of the different weights of the branches and how they adapt to your movements or whatever it is, and through experience start to do better and better and correct the generalization errors that are relevant to the problems that the agent is actually facing. And so it feels like in that sense, that while supervised learning can provide an awful lot, it can't be the full answer, because the full answer is about an ongoing process of verification and correction and discovering the solution to the problem through trial and error. And if we believe that the answer is already in the data set, that's a bit like saying the problems that we care about have already been solved, because otherwise you won't even see the solutions that you need. If you're trying to learn from some animal that's on the ground in the rainforest, and you're trying to you've got all the data that's ever been collected of all of those animals in the history of time, that might not be enough to tell you how to fly or to tell you how to climb to the top of the trees. You may just need to adapt through trial and error learning. And that's not to say there isn't a lot we can gain from those things, but it feels like the essential problem which RL faces, which we don't have in supervised learning, is that ongoing process of discovery, and maybe we do need to revisit certain aspects of what it means to do function approximation and the theory of function approximation in the context of continual, never-ending adaptation.
Thank you. You also mentioned model-based RL.
Yeah.
Perhaps part of the answer to sample efficiency. And the participants have been wondering, we had several questions over the last few days about the fact that model-free RL approaches at the moment seem to dominate in many challenging problems with high-dimensional observation spaces and action spaces, just empirically, and problems with long time horizons, things like StarCraft and Dota and robotic control. Do you see that model-based approaches like mu0, for example, will become successful in those domains? And what are the challenges to making model-based empirically as successful in applications as model-free methods?
Yeah, I think this is a great question. It's one I've been trying to grapple with actually since the beginning of DeepMind, trying to understand this question because it feels really fundamental. And although we've made maybe a little progress, I think it's still a big open research question. So what can we say so far? Well, maybe we can say that the big issue, why is it hard? Why is model-based RL hard, or when is it hard? And I think it's hard when the the state representation in which it's useful to represent your model is not innately given in the input that you're provided with. So if there in principle exists some model, but that model is only useful once you've kind of discovered the state over which the model is kind of jumping you, and then if only you had that state and the right temporal abstraction and so forth, then you would be able to sort of jump from there to there and from there to there, and the solution of your problem would be easy. So in principle, there exist models which may make the solution of many of our problems much easier, but the discovery of those models is very hard. And I think the challenges then come, I think, out from that statement, which is, first of all, how do we kind of discover the state representation for which models to which models should be applied, and how do we discover the jumps, the temporal abstractions? This is you should you can answer this maybe much better than me, Doina, but the jumps to which all of these models are applied seems such a fundamental question that until we address that, in some sense, we're going to have a very limited space of models. Like if we've got a very rich environment with agents that have are moving at some small time scale, well, models provide a lot. This is exactly the situation where you would think that reasoning in terms of long timescale models would be very effective, but what we tend to do is restrict our attention to single-step models, and in doing so, it might just be that we're limiting the ability of model-based RL to be effective, because maybe there just isn't a lot you can do by reasoning at the single time step level. So Rich Sutton sometimes calls this the curse of the time step, that we need to break away from the curse of the time step, or it just seems, it feels that there's a lot of potential to build models and use them, and in as much as we haven't yet seen them kind of take over a lot of the in these kind of perceptually rich environments, I think that just suggests that we need to keep trying. Maybe there are many ways to do model-based RL, and we keep seeing new ones, and it feels like ultimately we want agents that understand their world, and a natural form of understanding is kind of model building too. And now what that means, I think, is part of the question of how you do the model-based RL. And so, for example, in Musero, we tried something which is a little different to classical model-based RL, and maybe there are other approaches which are out there which address some of the problems of constructing a state representation and using it. And let's just keep being creative and keep as a community trying to push in all directions. I think it would be a shame if we all clustered to the thing which happens to work right now, and all carried on doing the latest DQN or whatever it is, just because that's the thing which in the last run happened to come top of the Atari leaderboard or whatever. I think there's a huge space for fundamental advances, and if we kind of keep pushing on all the boundaries, then I think we'll learn more together.
So you mentioned that sometimes there may be some information that if the agent had it, maybe it could build the model a lot better, or it would really help. So there's always this tension between, do we provide this information to the agent, right, as some form of prior knowledge? Maybe we build it in from the beginning, or maybe we give it a prior, or maybe do we give the agent data that's been obtained from experts, people, and so on, and then let it do imitation learning, and then only afterwards do RL. What's your take on the role and the pitfalls of using prior knowledge and prior data, both of these things, in RL agents, deep RL agents?
Yeah. So, look, of course, there's always going to be situations in which the agent's going to face situations that are completely novel, and it needs to just succeed first time round. Otherwise, it dies or whatever. Like the gazelle is born, and it's if it can't run, it's going to be eaten by the lion. So there are going to be situations where prior knowledge is necessary. But I think let's think about where we're going with AI, and it feels like where we're going is towards applications and environments with increasingly long lifetimes, and towards application environments that are increasingly complex and large and rich. And I think in those situations, the role of prior knowledge becomes less, and the role of ongoing learning becomes more. And so, I don't want to say that the prior knowledge doesn't play a role, because of course it does, but that the real challenge that will scale, coming back to the scalability question, the scalable aspect, the part which is going to give us the huge wins is an understanding how we continue to do better and better with more and more experience. And that part feels like it's kind of, it's almost orthogonal to the question of where you start. And because, wherever you find yourself at any point in learning, you need to just be able to continue learning and continue adapting and do better and better and better. And only in that way will we be able to deal with these very rich environments. And again, it comes back to that point from earlier, which is, okay, then you might say, well, what if your prior knowledge was so vast that it contained everything you need? And I think that might be just not feasible. I think that it's literally infeasible that some prior knowledge can contain everything you need when the things which are facing the agent in the future are very, very uncertain in a very rich environment, because you just don't know what path life is going to lead you down. And only when you get there do you discover that that actually the really important skill you need is to be able to build out of ice if you're in the Arctic, or out of jungle foliage if you're in the rainforest.
Thank you. So, modern RL, especially deep RL, is driven a lot by high computational resources, right? Lots of data. Do you think that this is a problem moving forward in terms of reproducibility and or the research that's being carried out in academia? Do you see reinforcement learning moving into a setup where it's perhaps mainly carried out in industrial research labs? This is a question that has, again, been recurring over the last few days, especially from more junior participants.
Yeah. So I think it's a really important question. I think what we're seeing, I think, is that if you're in a situation where you're working on a very large application and you're trying to demonstrate at the frontier of that application that you can produce the first thing to crack a particular giant challenge, that it is useful to have large-scale computational resources. And I think that there is an advantage to being within industry or having industry support in order to being able to do that type of research. But that's just one type of research. And there are many, many types of research. And, I've been really encouraged actually over the last few years to see the number of successful academic institutions and PhD students who within a more limited budget are able to really discover fundamental ideas in RL, pursue those ideas, do good science, demonstrate within that good science that their idea works really well, and that ability to do science, I think, is absolutely within everyone's capability and not limited by budget. And in a sense, I think the goal should be to demonstrate through good science that something works, and if you can make that demonstration so clear that we're sure that it will be reproducible in other contexts, then the likelihood is much greater that the people who do have access to the the bigger data and bigger compute budgets will build upon that research and use it. Everyone's always open to new good ideas. So in that sense, there's a pathway for everyone to be part of the next AlphaGo or AlphaStar or whatever it is. And the pathway is doing good, clear science and discovering something and showing that it here's a clear idea, here's a demonstration that clear idea works really well. do it in whatever context best makes that demonstration apparent and makes the most compelling case that this thing really is effective in a general idea which can work across a variety of different contexts. And if that case is made, I think it will make its way into the big applications.
That's really useful advice, and it's a great segue into some questions, I guess, that are geared towards advice for junior researchers. So participants were wondering, what do you recommend as a good way to learn reinforcement learning for somebody with no prior knowledge? So let's say that they are reading the classic RL book by Sutton and Bartow. They're watching some of the lectures on YouTube to learn some of the basics. What is the next step afterwards, after that?
Yeah, so this is a good question. I think there are many possible next steps, and some of them include, and I think maybe the clearest one is just to become curious as an individual, to become curious enough to start trying some of these ideas and to pick something which maybe you find personally fascinating, and start to explore reinforcement learning within the context of that application or environment. And I think through a process of exploration, I think and curiosity, I think it's possible to learn an awful lot. And I think that for some people at least, that will lead you to some of the other possible things which you could do, which would be to read papers on the subject of reinforcement learning, and there are various places that do suggest a variety of kind of classic papers. I know, for example, OpenAI has a list of recommended reading material if you're interested in getting involved in deep reinforcement learning. There are various other sources you can look at for that. There's and if this is something which you really engage with, what's the next step? Well, how far do you want to take this? And if you engage with it to the extent that it's something which you really want to devote serious time to, well, then you've got more options available, which are to actually start exploring whether you want to do this in the context of academia or industry, to really choose to do a master's program or a PhD program in reinforcement learning, or to apply for a position in one of the industrial labs, to work in the context of a place that's doing reinforcement learning. And I think those are possible, but as things are kind of taking off, I think the first thing helps a lot in getting the second. So if you kind of can demonstrate that you are someone who really cares, and it's like when you're talking to someone and you're trying to get a PhD or whatever it is, and you can say, well, here's this thing I did, and I really made this work, and I really cared about this, and now here's my discoveries. It puts you in a much stronger position. So I think just that a process of curiosity and see where it takes you, and maybe it will take you to one of those places, or maybe it'll take you away and you discover actually maybe this wasn't the question that you thought it was, and you find something else more appealing to you, although I can't understand how that could happen. But anyway.
So you've worked on many new algorithms, very successful algorithms, DQN, deterministic policy gradients, right? Many new ideas, fundamental ideas. How do you come up with these ideas for research? Is it a light bulb moment? And if it's a junior student in the field, how do they find the really nice, good, juicy research problems? And how do they recognize that something has the potential to be important?
Yeah, that's a really good question. I think it's really hard. I mean, if you look back over the course of what the research that's been done in AI, and ask how much of that older research is still relevant today. Some of it is, and some of it's absolutely critical. But I guess the goal is to try and find the nuggets which are still going to be meaningful in years to come. and I guess I'm searching for those, and I don't know if I found any yet, but I'm still, you know, on that search, and so it's about then how to identify those. I think I would come back to, you know, these questions of making sure that whatever it is you're working on, that before you put a lot of time into it, that you believe you're working on something which, if it was successful, would be a meaningful contribution. And by meaningful, meaning that you know, it has some of those properties we were talking about earlier, like scalability, something which is, if it works, you know, will this scale up to work over longer and longer timescales? If this works, will it apply to many problems other than the one I'm facing right now? You know, is this something which has breadth and depth of applicability? And if the answer is no, you know, don't be afraid to move on and to think again. It's really hard. And, you know, I think the other thing to say is that when you look at people's publication lists, well, I guess you see the things which worked out, but you don't see the litter that's strewn along the path to get to those points. And so I think it often feels like after the fact that, oh, you know, this person had this really clear idea that just, you know, must have just come out in this way. But often the reality is not like that, that there's been a whole process of incremental gains of understanding until the point when this thing is actually written up and everyone else gets to see it. It feels like there was that clarity to it, but the reality was that it's, you know, it's an ongoing struggle to find clarity for all of us, and that just recognizing that that's you know, a pathway, that it's not something which it doesn't just appear in a puff of smoke and, you know, with a genie that comes out of the bottle and tells you the magic thing to do. It's a struggle, and we have to continue struggling to find the clarity. Yeah, and I try and do that, you know, every day, try and make things a little bit clearer, and that, you know, I hope that we'll all come back in years to come and take all those things from the past and say, well, those were just the beginning, and here's a much clearer way to think about those, and with new algorithms, and, you know, the journey continues.
So let's say you have an idea which you think is a good idea, and now you want to turn it into, I don't know, an ICML paper or an URIPS paper or something like this, because you're a junior student and you want these publications. How long is a research cycle, typically, from idea to actually seeing something through?
Yeah, it can be long. You know, I think I think there's this sense in which stuff just works and then you publish it, and maybe it used to be like that in the old days, I don't know, but I've certainly never experienced that. And it feels like, you know, if you want to have something which is really good, you have to work really hard to make it good. And so, you know, it's not just for the big applications. I mean, certainly for, you know, if you look at AlphaGo or AlphaStar, we're talking, you know, 2-year multi-people efforts to try and get to the point where something was good. But even for, you know, the vast majority of papers I've been involved in, I would say, yeah, often maybe I want to say you know, a year maybe is like it can be, and sometimes longer. You know, sometimes I right now, the paper which I just wrote up was something I've been trying to grapple with and clarify for maybe 5, 6, 7 years, and I feel like I've been wanting to write this paper for all that time, and it's sort of gone through various iterations along the way, and now I feel like we've reached the point where we can say it clearly enough to be worth saying. So that's an extreme example, but you know, it's sometimes it's I think it sometimes seems to, like, whenever you look at someone else's work, it seems like it particularly, you know, conditioned on something having been published, it always looks easier in hindsight than it was to get to that point. And you know, and the reality is we're all struggling. We're all making mistakes. We're all, you know, trying experiments that fail. We're all starting at the beginning with really toy experiments and checking if they can work at all, and trying to, you know, particularly if you're trying something, you know, the more fundamentally different it is, the more you sort of have to back up to something really simple and just see if this thing, like, does this even work on a 4-state grid world, you know? And you have to take the time and be patient sometimes to make these things work. Now, it's not always like that. I know that there are ideas where people, you know, they come up with their one change and they try that one change on something and it works. But I think it's okay to acknowledge that the norm is that you have to work hard to get something to go well. And I think maybe something we can do better as a community is making it easier for junior researchers to be able to kind of exercise their ideas in a way that's likely to lead to, you know, maybe the idea doesn't work, but at least is more likely to lead to a high quality experiment where we trust the results of that experiment. And I think that the way in which we can make those things easier is through, you know, sharing clear environment, sharing clear agents, sharing clear understanding, and having support mechanisms to, you know, help you know, teach and support people through that process, which you know, we all go through.
So, you know, suppose you had a great idea, what you thought was a great idea, you implement it, and then the results are just not as good as you hoped, right? Maybe they're okay, they're not terrible, but it's not state of the art. Do you still publish a paper about it? Do you just move on? Do you, you know, do you try to push it to a refereed publication, just put it on archive? So what's that decision process like?
Yeah, that's a good question. I look at it. I think it's different also whether you're trying to, you know, have your first publications as a PhD student, or whether you're sitting on a bunch of publications and you know, its publication isn't necessarily important. So you know, within DeepMind we have the luxury that we don't need publications, and so I've typically waited until I feel that we have something worth saying before publishing. And part of having something worth saying is having the validation that the idea really was a good idea. Because without that validation, you know, it's easy to say an idea, but to know that that idea is good, how do you do that? And at the same time, I feel like we've got into a slightly unfortunate situation in our community where it feels like unless you have some kind of validation on, you know, what people consider like proper RL environments, that that the idea isn't, that the paper isn't worth publishing. And that to me seems a real shame. I think that we're losing good ideas in the community because we're over focused as reviewers on oh, well, this person hasn't shown that, you know, a 20% improvement in median performance in Atari, this can't be a good idea. And I think as reviewers, you know, we can take the opportunity to be more open-minded in what constitutes a validation of an idea. And there are many ways to validate. And I think, you know, choosing validations which are appropriate to what is being said seems perfectly reasonable to me. And so, and also, you know, what's reasonable as a validation for a junior researcher in an academic institute might be different to what's reasonable from sitting within DeepMind, where we can run, you know, a billion-step long experiment.
That's great, thank you. Somebody was wondering how you divide your time, your research time between, let's say, reading papers, writing papers, just ruminating ideas, coding and running experiments, talking to other people. Like, what are the major activities and about how much time do you spend in each?
So the funny thing is that maybe it's just my personality, but I can't give an answer to that because I keep experimenting with it. So I'm never happy with whatever balance I have. I always feel like I'm not using my time well. And so what I tend to do is experiment. And so, you know, people will, from within DeepMind, will know that there have been times where I've literally deleted every single meeting from my calendar and said, you know, that's taking too much of my time. I want to have more time for these other things. And then there have been times where I've, you know, stopped coding altogether. And there have been times where I've, you know, it's just, I try and experiment, and I've been through different processes. And sometimes I engage with a project like, you know, AlphaGo or whatever it is, where I tend to put a lot of myself into it for a long period of time. And when I try to keep that focus going, it often pushes aside a lot of the other activities that whilst I'm doing that. And then at another period, I might come back and try and spend more time exploring and reading and understanding. And I mean, the one thing maybe I can say is that consistently over time, my greatest regret is not having read more. You know, whenever I always feel like reading is the one activity that always feels the least urgent relative to all your other priorities in the short term, but over the long term has the greatest kind of benefit long term, you know, just to your own understanding and just making sure the inputs are still feeding in, so that if those inputs aren't coming in, then it's harder to just keep things ticking over, at least I find. But, you know, everyone's different as well. And that's just, yeah. So I don't even know. I keep experimenting, and maybe other people have advice for me, because I would love to know the, the right way to do that.
So in terms of reading, another theme that's emerged during the last week is sort of the onslaught of papers that are coming out all the time, constantly, lots of papers. Is that overwhelming, like the number of papers? How much time do you usually spend reading a paper, and how do you sort of extract and remember what's meaningful out of the papers that you read?
Yeah, that's a great question. I mean, I think the first thing to say is, you know, we've just got to accept that there are too many papers to be able to read all of them. You know, that's just not, we're way past the time where it's even possible to track what's going on as a whole. So I think, you know, the mechanisms by which things bubble to the top are sometimes useful. So things do naturally bubble up when you go to, you know, I enjoy running the DeepRL workshop, for example, because that's a place where a lot of the interesting things over the last year bubble up, and I get the opportunity to look at them. So conferences are a great way to get that. Talking to people, finding out what they find interesting is a great way to identify the interesting papers. Another piece of advice which I've heard, which I like, is to take a paper, don't read the paper, but look at the what they're citing and read those papers instead, because the things which are most commonly down there are probably the ones which actually contain the core ideas, which are important and relevant. How do I read a paper? I have a big bias towards trying to find the idea in a paper. So I try to come into other people's work with a positive mindset and look for the good idea in the paper. Same for talks, that, you know, don't go in looking for what's bad about a paper or what's bad about a talk, because, you know, you'll just come away with a load of grumbles. But if instead you look for what the good idea is, then you may come away with something which is helpful, even from a paper which is otherwise not containing things of use. And I personally, when I read, spend much more time on the ideas section of the paper than the results section of the paper. Sorry, everyone. But it depends on how close I am to the topic. So if I'm trying, you know, it's also, there's like a pyramid where some things that you're actively working on, I want to know every single detail about how they've done something, and I'll read a paper in much greater depth, including, you know, every experimental detail, if it's the thing which I'm at the top of the pyramid where I'm most focused right now. But for things which are kind of broader and further away from that, I'll often just try and get the idea, you know, get the understanding of what they're doing, and sometimes even just skip the results for those ones. And yeah, that's how I read.
This is really useful advice. We're coming towards the end of our time. So I was just wondering if you have any parting thoughts about the current state of reinforcement learning, the future for the field, or any further advice for the young researchers we have at the school.
I just feel really excited. I feel like we're just at this super exciting time for anyone coming into reinforcement learning where we're at this time where it's like exactly the sweet spot in when people look back in history, they'll say this was the sweet spot where the ideas started to work, and we had access to the technology and infrastructure to make ideas like work, and we start to see some successes of reinforcement learning. But before everything is kind of cracked, and all we're just in that sweet spot where there's a lot of discoveries being made and all kinds of interesting things happening. And it's not just a sweet spot for reinforcement learning, but if you take what I was saying seriously about reinforcement learning being the core problem that really defines what we mean by AI, well, this is the sweet spot for maybe the greatest challenge in facing science, that how do we understand and implement intelligence? And we're in that sweet spot, and we have an opportunity to be the people that contribute to that progress. And I just find that immensely exciting. And when I wish I could see everyone, but when I am able to attend events like this, it's very encouraging to see the people that are coming through, and there's these great new minds coming to bring their thoughts to bear and their perspectives